the next method for solving a system of equations is called the substitution method. And sorry that the packet is out of order. It doesn't really matter, but I'm going to try to stick to the order that the book goes in. Now, I typically prefer the elimination method to the substitution method, just due to usually the substitution method is a little bit more messy algebraically, but there's some situations where the substitution method can be easier. So it will just depend on the way in which your equations are set up. And basically the idea behind the substitution method is you're going to take one equation, plug it into the other one. Since both of them have to simultaneously be true, and that's the whole idea behind a system, we should be able to use them together. And if we put them together, we can often replace one of the variables in order to solve for the other one. So step one of using substitution is you always want to solve one of the equations for a particular variable. So like when I solve these for y above, that would actually be very helpful for the substitution method, specifically, because notice that both of these equations say y is equal, and since y is the same y in both equations, I want to know when those two lines cross each other, so the y value should be the same. Basically, if I were to just set negative 2x plus 3 equal to negative 5/3, what I would get is the solution to that equation. So let's just do that, and let's you'll see what I'm talking about. But basically, if we just set negative 2/3 x plus 3 equal to negative 5/3 x, this should allow us to find the same answer that we found. But again, this would be an algebraic strategy as opposed to a graphical strategy, because we're not, we're actually solving it by an algebraic method. And if I multiply through by 3, that will make this equation a little bit easier. And then if I were to add the negative 2x to both sides, that would be negative 3x. Dividing by negative 3 would give me x is equal to minus 3. And notice that that is consistent to the answer that we knew was valid, was a valid solution to that equation. But it doesn't, notice I don't get the full answer, because when I substitute y, or in this case, it's sort of like I'm plugging one into the other. I'm losing out on my y. So, but in doing so, I'm solving specifically for x. Now, if I want to know, well, what's the corresponding y value? Well, as we know in an equation, if I know the x value, I can plug it in to find y. So if I were to then just to substitute that back into either equation, you can always, we sometimes are calling this reverse substituting. But when I reverse substitute, I can plug it into either equation. Let's just say the second one, because that one's easier, negative 5/3 x, to figure out, well, what would the corresponding y value? And of course, negative 5/3 times 3, negatives will cancel, as will the 3's, and that will leave me with y is equal to 5. And I get the correspondent solution that, again, we already knew about, because we solved it by graphing. We solved it just by guessing, or by verification. But that's the essence behind substitution. And the goal in general, if we're trying to solve a general system of equations by substitution, you always want to have it either solve for x or y to start with. And in any of those cases, if you do that to begin with, basically the idea is you're always plugging one into the other. Because in number 3, the first equation says that x is equal to all this. And then in the second equation, I have 2x minus 3y is equal to 16. Well, basically, this first equation is telling me, well, x is equal to all this stuff based on y. And what I can do is I can just take that x and replace it with what x is equal to. And we call this substituting because I'm like taking the entire x and I'm substituting one equation into the other. And always use parentheses when you're substituting, because when we write 2x, that means 2 times the whole value of x. And x is more than one thing, so I want to make sure the 2 is multiplied to both things. And whenever you're doing substitution, always recommend using parentheses around what you do substitute in. So that would give us negative 12 minus 4y minus 3y is equal to 16. And now we have just a single equation with one variable. This we can always solve by isolating y, combining like terms, and adding 12 to the other side. Then if I were to divide by negative 7, that would leave me with negative 4. And again, I get one part of my solution. So the idea is I'm going to take one equation, substitute in the other, and in doing so, we're going to get rid of one of the variables. Now I have an equation of one variable. This is solvable. I get my first part of the answer. Then to find the second part, and in the case of substitution, I always recommend plugging it into what you substituted, because that one literally we had x solved for y. So that one will always be easier to then figure out x. But you can plug it into either equation since, again, both of them have to be simultaneously true, which is why either one is fine. Once I know y, I just need to find the corresponding x. And x would be equal to -6 minus 2 times -4. That would be -6 plus 8, which is 2. And then I get my final answer. Usually we express it as an ordered pair, which is common for a point on a line or an ordered pair of data where we need to know both x and y. And I'll leave number 4 for you to practice on your own. See if you can get it. And again, if you do get stuck, you can. The reason why we like to learn different methods is if we ever get stuck doing it one way, we have a different way. We have more than one way to think about it. And again, we could always check with our calculator as well.